Okay, are you ready? All right. Welcome to another member seminar of this week. Still, we have some new visitors. So member seminar is core seminar series of BIMSA. It's a colloquium series where professors of BIMSA explain their research. It's great pleasure to have Professor Kimyeong Lee, who is going to talk about 6D superconformal field theories and literally string theories.
Thank you. So few years back at a party, one of the liberal art professors asked me, "What are you doing?" And then I was ready to talk about this kind of things. Then I realized it's a bad idea. So I said, well, think about beginning of a civilization where farmers, instead of eating all the crops, saved some of them and planted it next year. Why? Because they know the nature and how to get the profit out of nature. So what I'm doing is basically extending our human knowledge of the nature. So we know a lot about nature nowadays compared to early farmers, but still we don't have a complete understanding of our nature. And we are trying to extend our knowledge. And my research is in the front of that discovery. Right, so let's start with our world, four-dimensional space-time. And there, this Himalaya from Tibet side, not from the Nepal side. And there we have nature. It's in space-time, and then there's a space there, location, and then time flows. Wind is blowing, cloud is moving around. Now we are looking at this nature, and we want to do something about it. So that's a job of a physicist. Everything around us, all the physical world is our game. And so physics covers the nature, which is made of events in space-time. And the event evolves matters and forces and evolves with time. So we are interested in finding the underlying structures or laws or theories. And as we know now, all the matters and forces are made of elementary particles and elementary forces. And the standard model, which is written in quantum field theory language, captures the law of particles and forces. And law of gravity is written in terms of general relativity, which is not quite quantum field theory. It is next to quantum field theory. Now, study of quantum gravity led to string theory. So there, where we are, our understanding of our nature, and we want to extend this boundary of our knowledges. Now let's start with classical field theory, which is bit familiar. So we are living in four-dimensional space, and every point in space-time, there is some field, like electric field or magnetic field. So for example, at this point, there is a magnetic field coming from the Earth's magnetic field, and it's vibrating, so it's changing with time. So there are such a field permeating through the space and time. And then these fields are vibrating, moving around, making waves. And so one of the simplest things is that it's not interacting, but it's freely moving. And those are free field theories. And it's like a wave on the surface of the lake. And then they are moving around, and their equation is captured by wave equations. So here is the wave, and the waves are moving around. And this equation is very simple, sine wave moving along the space-time. So this very simple equation captures the free wave. In this case, there's a mass term for this waves. So it's more like standing wave. You can do it. Now, but nothing is free. They are always interacting with each other. So one can introduce interaction between this classical wave. And the best way to capture the interaction in wave equation is to introduce some nonlinear terms, or from Lagrangian level, where Euler-Lagrangian equation leads to this wave equation has nonlinear terms. So that's a very easy way to capture the interaction between free field. So that's classical field theory, but we are living in quantum world, and so we have to quantize these classical field theories. So here's the wave where we see even our sound is a wave. start from my voice to hitting your ears. So we are living in this ocean of the waves. Now we want to do something about quantizing these waves. Now, simplest quantum field theory discovered this quantum electrodynamics, which is the theory of the electrons and electromagnetic fields. And the way Dirac quantized, even though Planck and Einstein quantized it, but Dirac quantized the Lagrangian properly. And the way he quantized, then what he got is the interacting particles. So if you quantize the free field, then for even field, you generate identical particles like electrons and photons of given mass and given quantum numbers like spins and charges. Now, quantum field theory is a theoretical framework for interacting particles and one kind of particle for each field. And QED, quantum electrodynamics, is theory of the electromagnetic field and electrons. So there are two kinds of fields, gauge field for electromagnetic field and then spinor field for electrons. And the electric and magnetic field is given in terms of field strength. And then interaction between electron and the gauge field is through this nonlinear term, which comes from a covariant derivative of the field. So Lagrangian for electromagnetic field and the spinor field is given in very simple form. So this is quadratic in gauge field, and this is quadratic except these interacting terms. And that nonlinearity lets the interaction between photons and electrons. And people have studied this theory from, say, 40s, and people understand this theory very well. Now, that's the beginning of the quantum field theory, and people have looked at the further of the nature, and what they discovered is that quantum field theory is characterized by symmetries. Like, for example, most fundamental one is space-time symmetries, where our space-time is invariant on the physics is invariant on the space-time translation, and also rotational symmetry. So physics is invariant on the rotation of the systems, and also is invariant on the constant velocity frame change, which is Lorentz transformations. That led to these symmetries led to conserved quantities like energy, momentum, and angular momentum. And also they play this conserved quantity play a role of the generator of these symmetric transformations. So symmetries, these space-time symmetries, and then there are additional symmetries called internal symmetries. Like, for example, they led to conserved quantity like baryon numbers, lepton numbers, and electric charges, and so on. Now, QED has a additional local gauge symmetry, which tells us the gauge field transform under this local gauge transformation. Lagrangian is invariant, especially field strength, and is invariant, and also spinor field transform with a phase, and the covariant derivative transform as a phase. So the whole Lagrangian is invariant. And those principles are very important in deciding what kind of theory you have. And when we are writing down the theory for the nature, these principles guide us to discover the law more precisely. Now, among which most important property of this symmetry is the rotational symmetry. So as you may heard of, when we rotate 360-degree rotations, I'm returning to my place. But we are living in three-dimensional space, then 720 rotation and the 360 rotations are different. So that there are particles which know the 360-degree rotation is not identity, and those are called the fermions. And they carry half-integer spins, and bosons carry integer spins, so it doesn't know about 360-degree and 720-degree rotational difference. Now, bosons satisfy Bose-Einstein statistics, and so you can have Bose condensations in low temperature, and fermions satisfy Fermi-Dirac statistics, so it satisfies Pauli exclusion principles. So one of our existence is crucially depending on Pauli exclusion principles. All the chemistry is possible because of this exclusion principles. And the pressure we are standing on this ground is due to Pauli exclusion principles, not due to electromagnetic forces and so on. So by understanding the nature theory of the natures, we understand what's going on around us. Now, one could naively say that all the forces are delivered by bosons and all the matters are made of fermions. So you think it's a physics job and the mathematicians don't care about fermions and bosons. Not so quick. So let's think about bosons and fermions in number theory. So partition function for a given quantum system is infinite temperatures defined as a trace over Hilbert space over e to the minus beta h, and h is Hamiltonian, and beta is inverse temperature. And this partition function has been studied for entropies and phase transitions, and that's one of the most important quantities you can define on quantum system. Especially for harmonic oscillators, energy level is linear, and then h bar omega, which is a harmonic oscillator frequency, and that can be regarded as a sort of energy gap between each levels as a log x. If we define that way, then partition function is given in terms of this series. So minus beta over 2 is due to vacuum energy, and then you have vacuum and the first excited state, second excited state. If you go to quantum field theory, this is like a vacuum, 1 particle, 2 particle, 3 particle. It's a bosonic particles. And when you sum them, all the particles, this partition function becomes x to the minus beta over 2 over 1 minus x to minus beta. Now let's look at the Riemann-Zeta function, which is the sum of the 1 over n to the s. You can famously, this can be written as a product of 1 over prime number is 1 minus p to the minus s. Now you can see right away, this is a partition function of bosons. There's a bosonic particle for each prime number, and whose energy is log p. And then its partition function is exactly zeta function. So zeta function is some sense finite temperature partition function for prime ones, this particle, bosonic particle for each prime numbers. Now, what about 1 over zeta function? Then that is just a product of 1 minus p to the minus s. Well, that's given in terms of sum of n and mu n over n to the s, and the mu n is called the Möbius function. And if you look at Möbius function, it has complicated formulas. But if you look at it, it's a fermion partition function with Witten index. For each single fermion, we have minus 1 to the f. So each prime, now for each prime number, there are fermions. So because of Pauli exclusion principle, either you can have 1 vacuum or 1 fermion, no 2 fermion of identical state. So that's why each prime Hilbert space is made of the vacuum and 1 fermion for single prime numbers. And the minus sign comes from this Witten index. And so Möbius function is basically one which takes care of a Pauli exclusion principle. Plus sign is taking care of this Witten index. So if integer n is made of product prime number, and if the same prime number appears twice, it's 0 because of Pauli exclusion principle. And if the number of prime number is odd, it's fermion, so it's minus 1. If the number of prime number is even, its boson is plus 1. So even when people are doing mathematics, secretly they are doing physics, and they don't know that. So a lot of times physics simplifies math some sense. Right.
Can I ask you a naive question? So how many fermions do you have? Infinitely many?
Yeah, for each prime number.
Is that so? I thought the world is finite.
Well, we are mathematical game. You can have anything you want. So,
but how is this then being described?
Oh, so right. So the hypothetical particle primal is living in metaphysical world. So it's not real world.
Okay, so you are still doing number theory, not physics.
Not so quick. So our ambition. So everybody comes in, you are physicists, don't touch my field, kind of crap. So I would say our ambition is endless. There's no limitations. And the mathematician draw the line. This is my field. What?
Okay.
I'm curious. I'm willing to discover things, and this is one of directions. So,
Oh, just kidding. Thanks for the answer.
so any other questions? Right. So among nature now, we need sun now. It's getting cold. The sun is hitting us very nicely, and one of the reasons is that there's a fusion of nucleus inside the sun, and one of cause of this fusion comes from the deuteron nucleus and the tritium nucleus are merging together and make a helium nucleus plus neutron. And because of this, even though initially they carry electric charge, both carry plus electric charges, so they are repulsive Coulomb, repulsive force between them. But when they get close to each other, they merge together and become a helium nucleus plus neutron. And it has a lot of energy left over, so it kicks out huge kinetic energy. That's how the sun is heating up. So this kind of very, very strong interaction in very short range arises from some sort of interaction between neutrons and protons. And people discovered that protons and neutrons are made of quarks, and each quarks carry color charges, which is SU3 color charges. And when they're interacting each other, they interact very strongly. So this strong interaction is part of our life food. And we have a pretty good understanding of this strong interaction. Now, so people managed to write a theory on this strong interaction in the early 70s, and that's called the quantum chromodynamics. And QCD means that it's a SU3 gauge theory. SU3 is some sort of a Lie group where n by n unitary matrix whose determinant equal to 1 is called the special unitary group. And especially when n equals 3 is called the SU3 gauge group, SU3 Lie group. And this here is SU3 Lie group as a gauge matrix. So it has 8 gluons, which is belong to identity representation of SU3. And then there are quarks with 3 colors, red, green, blue. And then the gauge field is written in non-abelian form. And the field strength has nonlinear terms. And plus Lagrangian for these gluons, plus the interaction between quarks and gluons through covariant derivative. Now, this theory has a local gauge transformation on the SU3 transformations where U is unitary and determinant equal to 1, and gauge transform in this way, and the covariant derivative also transform in uniform A. And this theory has been written, and especially this coupling constant, this pine structure constant turns out to be not constant when you probe the series. It changes with momentum, and it's called the running coupling constant. And people managed to calculate this. And this is a theoretical prediction, and this is experimental measurement. And they match each other pretty well. And one of the key features of this theory is that as you go to high energy, interaction is getting weaker and weaker. So it's called asymptotic freedom. In addition, this theory is color confinement and chiral symmetry breaking and so on. So there are highly non-trivial, non-perturbative physics whose physics is not completely understood yet. Now, as I said, the standard model, which captures the physics of elementary particles and the elementary forces, is very simple. Unlike a periodic table, which has like 100 elements, this one has a pretty small number of elements. So there are quarks and leptons, 6 kinds of flavors for leptons and quarks, and they are all fermions, and they form say matters. And then there are gluons, photons, G boson and W boson. They are vector bosons. They carry the forces. And then there is Higgs particle, which generate energy and also beat forces, and gravitons. So as I said, a strong interaction, there's SU3 gauge symmetries and electroweak symmetries, which is related also fusion of the nucleus has SU2 cross U1 gauge symmetries. So total gauge symmetry is SU3 cross SU2 cross U1, and plus gravity, which is related to curved space-time. And theory can be written in rather simple form. you can add a few indices, then it makes the whole series. So physics, I mean, in mathematics, something is very simple. We don't need heavy mathematics. But the theory, discovering this was, of course, very tortuous. And the experimental confirmation is also very difficult. Many Nobel Prizes hung around somewhere. And this is Yuga coupling. So theoretical physics, even though we are using mathematics, I realized as I talk more to mathematics, we are a bit different creature. And also theoretical physics is rather recent. Only middle of 19th century, name physicist was invented. Before they were all natural philosophers or mathematicians. Mathematics, word it means just knowledge. It doesn't mean that structure the thing originally. So we are in that sort of process, and I don't know how theoretical physics will evolve in next few, say, tens of years. Maybe it will disappear, no more jobs for us, or we will all become a mathematician proving things. I have no idea, but we are still inquiring, exploring the world in our own way. Now, so let me start with now N=4 supersymmetric Yang-Mills theories. So we are looking at, we are leaving out of the phenomenology. We are looking at very special class of four-dimensional quantum field theory, which has supersymmetry. Supersymmetry means that theory is invariant on the exchange of bosons and fermions. I said there are fermions and bosons. They are all different. But what it means is that if I have, for example, gauge particles like vector bosons, then it has always spin half particle, which has the same quantum number besides the spin. So there's a sort of exchange of bosons and fermions. For quarks, there is a quarks, which is scalar particle, which is same quantum number as quarks and so on. So those theories have a more simpler theory, and so we can explore things more easily. And among which there is a maximally supersymmetric one, which is called the N=4 supersymmetries. So in terms of minimal ones, you have a gauge field and gauge nodes, and then you add 3 more gauge nodes into it. So they belong to order-entry representation. So there is, for single gauge field, there are 4 gauge nodes. So that's why it's N=4. And then there are 6 scalar fields. Now, Lie groups, as I said, in standard model SU3 cross SU2 cross U1. But if you look at the list of Lie group books, there are a lot of Lie groups, especially A, D, E are simplest Lie group, and I forgot B, B, C, G, 4, they are non-simplest Lie groups. And the Lagrangian is given in simple form, Maxwell-like term, Yang-Mills terms, plus there is topological term, zeta, trace F, edge F. And this topological term is possible because so the homotopy group of this Lie group is Z, which allows us these topological terms. So that the theory has a complex coupling constant, zeta over 2 pi plus 4 pi over G square. And physics on SVN theory has a very natural source origin from the string theory, that if I have n D3 branes, then those are some object in type 2B string theory, then parallel and D3 brane generate this SVN gauge series.
But G sub 4 and G are the same.
What?
In Langlands, G sub 4 square.
What?
That's the coupling constant.
That's coupling constant. Oh yeah, sorry, they are the same, right? They are, sorry, yeah. So you can see this coupling constant living on the Poincare upper half plane because coupling constant is non-negative. Right, so if I have 4 D3 branes, then there are fundamental string connecting them, and they generate a simple root, and they generate a thinking diagram. So one can relate easily to thinking diagram to brain diagram. And so these are thinking diagram for Lie groups or Lie algebras, and ABCD. Classical case, you have brain pictures. Now E-type and G-type, we don't have brain pictures. So we are thinking about those theories with arbitrary gauge group, because you say you are a mathematician, but we say we are theoretical physicists, so we have to play and see what kind of game nature is playing. When we want to play we have to see how nature is playing with these series. And one thing people found is that in Coulomb phase, you're breaking as you n gauge symmetry. You want to know these abelian subgroups. So in some sense, you are separating these three branes in finite distance. Then W bosons are like a fundamental string connecting these three branes. Now, it turns out, yes.
Stupid question. How do you count curly n?
Good.
Curly n versus the dimension n. Why is
Oh,
curly n?
Curly n is about related supersymmetry. So I said that for gauge field, there are 4 gauge in a field. So that's a supersymmetry. And I don't need to have it. On the other hand, the gauge group, I can choose any gauge group for given gauge series. So there are
I
two
think she's just asking what is the definition of curly n?
So n counts the for given Coulomb field or gauge field A mu, how many gauge field, how many fermionic field I have with the same representation. And I said maybe too quickly. So here, in terms of n equal 1 language, I have 1 gluino, but here I have 3 more. So then I have 4 gluino field for given gauge field. So, and then you need the boson partners, right? That counts the number of supersymmetries.
Very different ends and still the same curly force.
Right. Hmm? What's wrong with this theory? No, I didn't understand. I said I missed the B. Good point, but I missed the B. B is perfectly fine. Right, my finger missed it. Right, that's why I included it. And if somebody's watching. Right. So you break this non-abelian gauge symmetry to abelian subgroups, and then you have W boson. Not only that, you have magnetic monopoles, which are solitons. And magnetic monopoles was proposed by Pierre Curie in late 19th century, and also by Poincaré. And the reason is that suppose we have magnet north pole and south pole. Suppose this magnet is very, very long, then I can ignore the north pole or south pole. Then one can imagine there's only north pole or south pole. Such object has been observed in nature. But in principle, such a thing is possible with the current theory. So if I have an electroweak theory plus gravity, I can have a magnetically charged black holes, which is perfectly possible. And nothing prevents it from happening, except that we haven't discovered by experiment. So similarly, n equal 4 super Yang-Mills theory has, without gravity, it has the magnetic monopole as soliton, which is called Tufte-Polyakov monopole solutions. And those objects has the same quantum number as W bosons, in the sense that because of colloidal zero modes, they carry vector spins. So monopole acts like W bosons. And Maxwell theory has this nice symmetry where I can exchange the electric field and magnetic field, and theory is invariant. Maxwell equation is invariant. But because we have only electrons, so theory is not invariant. Now we have magnetic monopoles. So once we change the W boson and monopole at the same time, theory is invariant. So this is called the electromagnetic duality, and especially n equal 4 theory has more symmetry, which is called SL2G, and especially S transformation, which transforms tau to minus 1 over tau, is electromagnetic duality, where coupling goes to 1 over coupling. And monopoles and W boson and monopole has this different simple root. So for given root, simple root, I have a dual root is 2 alpha over alpha square, and thinking diagram arrow changes. So for given gauge group, electromagnetic duality is more complicated, but magnetic gauge group is called the Langlands dual group GB. So Langlands discovered the magnetic group in late 60s. You see, he's doing physics. He doesn't know that. So of course, physicists, when people discovered this duality in the 80s, 70s, they realized that Langlands was there before us. But anyway, this duality changes B and C, and also this tau goes to -1 over ng tau. Ng can be 1, 2, 3, 4. And ng is 1 for simplest group, and for other groups, there's ng written there. And especially B and C can exchange under this Langlands dual group. But C-type theory has one more twist. Because C-type has half instantaneous range of theta parameters, not from 0 to 2 pi, 0 to 4 pi. So when you put theta to be 2 pi, it's self-dual on the SL2G with a factor 4. So that's, again, I don't know whether mathematicians observed that as their math. And whenever I ask mathematicians, it looks like we don't know about it, kind of. But this has been known to physics for the last 20 years. But maybe that's not the interesting part of math yet. All right, so we are done with 4-dimensional space. Now let's go to higher dimensional space, which is not part of our world, we think. But when they try to quantize the gravity, and then string theory appeared naturally. And then when we try to quantize the string theory, higher dimensional space-time appeared very naturally. So at the center of this higher dimensional theory is the M theory, living on the 11-dimensional space-time. And this constant quantum gravity theory. And at the corner, there are 10-dimensional string theories living there. And so one can imagine our world is made of the 4-dimensional space with some compact 7-dimensional space. I made it to be S1 close to Calabi-Yau 3. That seems to be easier to deal with. And that led to a lot of joy to a whole community of people. Also, 7D manifold can be interesting, like G2 manifold and so on. So if you think of this one as very small, then we wouldn't know there's such a space there. And so experimentally, we want to find that some geometry which leads to standard model in low energy. And so far, people haven't been that successful. But a fundamental object in M theory is made of the two objects, M2 brane and M5 branes. Remember, standard model has a lot of particles. Now we end up with only two objects. Hopefully, we want to describe everything out of these two objects plus some geometry. But we don't know that. But these two objects are like electric object and magnetic object of this three-form tensor field. Right. So knowing there's higher dimensional theory, so we can try to extend the quantum field theory to higher dimensions. So let's go to five dimensions. Now in 5 dimensions, one can write down actions for 5D Yang-Mills theories. And because action is dimensionless, coupling constant has dimensional length or 1 over mass. So Feynman extension, diagram expansion has parameter, which is dimensionless, should be coupling constant times some central mass energy or momentum, or central mass momentum divided by energy divided by this mass scale, which means that if a momentum is bigger than this mass scale, this is bigger than 1. So series is divergent, which means theory is not renormalizable, and so short distance physics is not well defined. So usually we throw it away such a theory, except take it as some effective field series. Now, in addition, because our space is 4-dimensional, we have instantons, and it leads to some conservative Yuan symmetries. Now, turns out this 5-dimensional quantum field theory can have a UV completion for certain cases when you have an n equal 1 supersymmetry, which means that 4D sense is n equal 2. So I have a 1 gauge field, then I have 1 gauge in a field and 1 scalar field. Together, they form n equal 1 supersymmetry in 5D. And then you can have some beta hypermultiplet, like electrons and quarks and so on. And together, for certain gauge groups, for all the gauge groups, especially SVN case, you can have 5D Chern-Simons terms, or SP groups, one can have discrete zeta terms. And then you can have a UV completion at infinite coupling. If you have usually infinite coupling, you cannot do any calculations. But turns out certain quantities you can do calculation using some localizations. So this is very interesting class of theories, and not all of them has a UV completion, only few of them have UV completions. And especially if you think about rank 1 SU2 gauge groups, and then n equal 1 supersymmetry case, if I have a 8 fundamental hypermultiplet, theory is complete in 60, not in 5D. there is instanton plays a role of color-to-crime mode in this case. And if I n equal 1 and if you have a 16 fundamental hypermultiplet, it goes to 60 little strings. Now, if you have a little more supersymmetries, which is maximal in 5D n equal 2 case, you have two rank 1 SP1, SP2 with discrete set of 0 or pi, and this leads with S of 5R symmetries. In this case, it leads to, again, 60 superconformal field theory. Right, so we are done with 5D. Let's go to 6D and see what's there. So I said the strong coupling constant limit of 5D theory is 6D theories. So strong coupling limit of the 10D type 2A string theory is 11D M theory with a large circle compactified. So T0 branes are color-to-crime mode of this compactification. T4 branes are wrapped the M5 branes, and fundamental strings are wrapped the M2 branes. Now, theory on T4 brane is 5D n equal to super Yang-Mills theories, and T0 brane on T4 branes are instantons. So this T0 brane, which is color-to-crime mode on M circle, has mass, which is proportional to inverse Yang-Mills coupling constant. Now, strong coupling limit means the radius of compactification is getting big, and then 5D M circle, this M circle becomes unfurled, and T4 brane becomes M5 branes. And the fundamental string connecting T4 brane, which was W boson, becomes M2 brane connecting M5 branes. So in strong coupling limit, 5D n equal 2 theory becomes 6E physics on M5 branes. So here we are. We have 4 T4 branes with fundamental string with thinking diagram in 5D now. We go to strong coupling limit, then T4 brane becomes M5 branes, and the fundamental string becomes M2 brane. So there's no W boson, but some string. Now, theory on this M5 brane is very strange. It has a 5R symmetries. In terms of tensor multiplets, so it has 1, 0 tensor multiplet, which is made of the 2-form tensor field instead of 1-form tensor field for gauge field. It has 2-form tensor field, and the one gauge kind of object, which has chiral on the 1, 0 of little group of SO4, which is SU2 cross SU2. And then you have a hypermultiplet again, quarks and squarks, but the quarks are like, again, chiral. Now, this P field has self-dual strength, which is 3-form tensor field is Poincare dual of its H, which means that this is both electric and magnetic at the same time. So that it's purely quantum theory, H bar equal to 1. So you cannot have a classical limit. And the M2 brane between M5 branes are self-dual source of this P-mini field. So it looks like a string theory. But turns out it's a quantum field theory in the sense it has well-defined energy momentum tensors, and you can do all kinds of calculations. It's not a Abelian theory, but there's no Lagrangian. People have been trying to write a Lagrangian. I know maybe 50 papers, all wrong, except mine. But, but anyway, it's very difficult, highly challenging. And one expects UV completed local quantum field theories, superconformal symmetries. Right, so this superconformal field theory is called the 60.
Is there any reason to expect that the theory will be local?
Well, yeah, there's no reason against it because the string becomes tensionless, then the stringy feature disappears sometimes. So this theory, 62,0 superconformal field theory, can arise from type 2B theory on R6 cross C2 divided by finite group of ADE type, which is through the McKay correspondence. They have a 2,0 conformal field series. Now, surprise is that I said it's not Lagrangian theory, it's not gauge theory, it doesn't have Lie groups. And the degrees of freedom, whatever calculation you do, turns out to be not dimensional Lie group related to the ADE type. It's product of dual Coxeton number and dimensional group. And that product appears as a prudential debris strange formula in the early 60s, where if I do the square of the Weil vector, which is sum of all the positive root divided by 2, then I get this product divided by 12. So this product appears. And so again, physics is saying hello to math. I think so. And also now 6D two-comma theory, compact final circle becomes the 5D Yang-Mills theory. So it has to know about Yang-Mills coupling. And Yang-Mills coupling is through this structure constant, which and if add to this quantity, then is product. And one find the code of VPS object where self-dual string connecting 1 and 2 M5 lane with a wave along it, which is F Karatang root. Or one can think about root is some junction of the self-dual string, and those object captures this n cubic business because SUN is n times n squared minus 1. So when n is big, it grows like n cubed instead of n squared. Now one can think about theory on torus. Then on torus there's SL2G, and that leads to naturally SL2G symmetry on n equal 4 theory in 4D. Now you can do the twisting of this theory on using our automorphism group of the thinking diagrams from 6 to 5D. The way you do it is, even though it's non-organic theory, you have to compactify without twisting to 5D, then compactify to 4D with the twisting, which is the ordinary twist the Caxton algebra. Then you make a S transformation, then you go to 5D, uplift, then that's how you get the twisting of the 6D to 5D. So it's all non-mathematical hand-waving way to get these answers. And so this is the list. Especially interesting one is if I think of SU6, then I get SO7, which is bigger than 6 by 6. Because it is not Lie group theory. Even if I do G2 twisting, I get a bigger group, SO7. So what are we interested in? There's probably you heard that there's something called the ADS-CFT correspondence. For given conformal free theory in large n limit, there is some ADS geometry with strings or membranes and black holes living. So even though you are doing quantum field theory, if you go to large n limit, quantum field theory knows about gravity. Quantum field theory knows about string theory. So you cannot separate them anymore. So a long time ago, oh, yeah, I don't need to think about string theory, quantum M theory. I will just do quantum field theory, but not anymore. So as soon as I'm looking at certain physics of quantum field theory, it is easier to understand from the M theory and string theory perspective. So gravity is right there. And people have all kinds of ideas about how gravity emerges from non-gravity theories, how space-time emerges from low-dimensional theories, and so on. So space-time seems to be not anymore fundamental. Gravity doesn't seem to be fundamental anymore. So it's a very profound ideas. And one of the things is, so local gauge invariant object in Euclidean R6, sort of the radial quantization leads to some geometric object in ADS7. Especially, one can, nobody has done so except for the n equal 4 super Yang-Mills theories. SU2 case, you can write down the operators and corresponding to black holes in ADS7, ADS5 space, and so on. So you can generate a local operator, you create a space, then boom, you are creating black hole in other space. So it's much more interesting at the, but what I have done is a simpler part of these stories. So I'm looking at the, usually we're interested in partition function. Again, trace of the e to the minus beta h with some few things added to it. So one can do the partition function S1 cross alpha, S5 of the this 6D series or R6. Or we can look at the small part of the partition functions. This object corresponded to black hole in ADS7 space. So this black hole will be zero temperature supersymmetric PPS object, but it's a black hole. But instead we are looking at a tiny part of it in the, say, North Pole. So I'm looking at T2 cross R4, omega deformed chemical potential turned on the angular momentum partition function. And again, that's exponential of entropies. And we managed to obtain the card limit, high momentum region of this angular momentum. And this black hole entropy on related to this geometry on this corner. And you can see dual Coxeter number times dimension group times momentum is appearing. Precise angular momentum J1 and J2 along the 1, 2 directions. Now, we wrote this paper about 3 years ago through the all different calculations. At the last day, when we are submitting the paper, I thought that there was something missing. So we decided to, by policy, we'll submit the paper this afternoon. This morning, I come to office and, oh, what's missing? Turns out, what was missing was that I'm going to a high momentum region of some twist theory. And twist theory is not losing any degrees of freedom. You are giving a little different momentum depending on how it transformed out automorphism groups. And so short distance physics or strong high energy momentum shouldn't change that degrees of freedom. And remember, this product appears as momentum is an integer divided by radius. So there is something invariant of an integer doesn't change, then there should be something invariant of after twisting. And that's what we discovered. So original theory, AD type divided by NG, which I gave you before, dividing should be invariant. We should get this product of the twist series. So for example, let's start this SU6. Dual Cox number is 6, dimension is 35, 6 square minus 1, 35, and divided by 2, then we get a 3 times 35. Now, SO7, which we get by twisting, we get dual Cox number is 5, dimension is 21. So if I multiply 5 times 21, it's 3 times 35 divided by 2. So it works for all the twisting, and you can go through. It's such a simple relation. So we've been asking mathematicians, probably some of you here, have you seen this before? If you so, where? Because this is some sense 101 of the Langlands dual, some sense. Very simple observation. And I know it's a tip of iceberg because if we look at black hole entropy, there are subleading terms. And also they all have to have that sort of identities. And also if we look at the less supersymmetric ones, they are more complicated version of these identities and so on. So this is a very simple identity. And I put in math overflows and so on. But unfortunately, the person I thought will know, Jim, the guy doing Lie algebra, Jim Humphrey, he passed away with corona. So I have to ask other guys, I guess, if you've seen this, this will be really interesting in some aspect. Right, so that's about 62,0 super conformal theory. So let's go to another world, 60 theories. So remember, we got started 5D Yang-Lee theory, and we go to strong coupling limit, and then we got a 62,0 super conformal theory. Now let's go to 60 theories, and then maximally supersymmetric one, which is 61,1 Yang-Lee theories, which means gauge field and this meta field helicity little group is different. So this one is 0,1 and this one is 1,0. So they have a that's why it's called the 1,1 Yang-Lee theory, and it's parity even because of this gauge has a different helicities. Now again, you can come with all kind of gauge groups. Interestingly, this theory can have theta terms, theta F trace for SUN type of theories, but it can be arbitrary irrational numbers. Or you can have theta equal to 0 pi for SPN series. And then this one theory has an instanton string instead of instanton. Now this theory you could ask, is it UV complete? Turns out not always. So all the theories are UV complete except the theta terms for SVN theory. UV complete only when theta is a rational number. Otherwise, you have to go to string theory or gravities. So you can see through the analysis, which Witten went through, many different ways, you can see easily that this makes complete its own only when theta term is a rational number. So there's some number theory going on there. So little string theory is we have a multiple, one way of getting is multiple NS5 branes. In type 2B string theory, then fundamental string on NS5 brane is little string, which is instanton string with tension given by fundamental string tensions. Or AD type, you can general gauge group, you can start from the M theory. Again, Mackay correspondence C2 divided by discrete subgroup AD type. Then you get a 70 Yang-Mills theory, which you cannot decouple the gravity, but you can compactify this theory further on a circle with a twist. Then you get a 60 Yang-Mills theory with a non-simplaced group. That's how you get the 1,1 little string theories. Now, 2,0 little string theories are a little different. This obtains from, again, NS5 branes in type 2A string theory. So suppose we have M5 branes, then there is a M circle we compactify now. So instead we get a conformal field theory, we get the little string theories. And the little string is M2 brane wrapping the M5 brane circles. So these small M2 branes connecting M5 branes are fractional little strings. And turns out 2,0 little string theory on a circle is T-dual to 1,1 little string theories, where winding modes and momentum modes are exchanged. And even though 1,1 little string theory is not always AD type, 2,0 little string theory can come only with AD type. So if you want to force a T-duality, then one has to twist the 2,0 series. So here's a 2,0 little string theory of the AD type. And now it's M circle, so simple root, including the affine root is appearing very naturally. And those are thinking diagrams for this extended AD type.
Why are they little?
Oh, because string theory lives on 10 dimensions. And when this string theory is vibrating, there are gravity appearing. But little string theory is living only 6 dimensions. When they vibrate, because they are decaying so quickly, they cannot generate gravitons. So they don't have gravities. So that's why it's the little guys. Even though there are lots of them. String theory, there are only 5 of them, but little string theory, any gauge group, so there are lots of them. So in number, they win. And so there are very natural way of getting this 1,1 little string theory by twisting the 2,0 series. And you can get all that. So let me conclude with some remarks. So we saw the very rich and the fertile landscape of theories. And we know roughly what's behind these hills, but we don't know the whole landscape. And we haven't explored the full landscape. So we are curious about what's there, what surprises are there. So for example, these theories are related to index functions, ADS, black holes, Calabi-Yau space, quantum curves, PPS quivers, integral models, generalized symmetries, 3D correspondence, and AGT relations, and so on. So let me conclude. Thank you for listening.
All right, questions?
So you had a slide where you sort of showed me that I was doing physics all along, but I was an analytic number theorist. But my question is, do you have an interpretation for the Riemann hypothesis? Because you were connecting the zeta function to something. So
Not so quick.
is there an interpretation? Like,
Not yet. I'm just a baby trying to learn Riemann hypothesis. I know a lot of people.
I'm not asking for a proof. I'm not
Oh,
asking
no.
for a proof. So what is the analogy there?
But what I found is that Riemann missed something
Okay.
in defining the zeta function. And I found, so remember, harmonic oscillator the vacuum energy. So Riemann zeta function has the vacuum energy from physics perspective. And so at the numerator, product of prime number has to appear. Right, so here, there is x to minus beta 2. So there should be p to the minus s over 2. So you have to have all the product of prime number divide then index with minus s over 2. So for a long time, I didn't know what to do with product of prime number. Googled it. Turns out to be product of prime numbers are 4 pi square. So Riemann missed times minus s over 2 is 2 pi to the minus s. That factor is there in some sense, and I tried that anything else is happening, but so I asked the Dan again, did you know about it? And Dan said, that's not important. Why? If it's important, somebody would have told me. Yeah.
Okay.
But so I was looking through all the L functions to see whether vacuum energy is taken care of, and the cerebral trace formula has vacuum energy taken care of properly. All the rest, no. So I don't know what's there. I'm just scratching the surface.
More questions?
So do you know why the M series only have M2 and M5 branes as the fundamental object?
Oh, there's M9 too, sorry.
Because M9.
No, there's M9.
Yeah, but then now why is these three?
Well, I have no idea. I mean, theory chose what it chose, then we have to follow the theory. I mean, oh, so there's an object appearing, even though a hypothetical world is a real object appearing in the theory. It's there and it's kicking and it's moving, and so we can touch it.
Dimension of it.
Two-dimensional object, the membrane, right? And the five-dimensional object and the nine-dimensional object. Yeah.
There is one question here. Another question?
Does the Higgs mechanism happen on any background space-time, or it's independent?
I think the Higgs mechanism happened already. That's why we are massive. And I don't know, our space covers space-time, right? So
On any curve?
yeah, so it may restore in high temperature or in other extreme environment, but most of the cases where we are living Higgs mechanism happened, and we are living with Higgs particles and massive quarks, leptons.
Yeah, I just wanted to ask about this 1,1 youngness.
Right.
You said it's basically you incomplete when you have
Right.
the theta parameter to be rational.
Right.
So what was the interpretation of that again?
Is there a quick string theoretic?
Right, so
way
it
to
is
sti-
very
to-
natural to construct. So remember I said the 70 Yang-Lee theory I obtained by AD. Then when you try to construct the 60, I have to have a discrete set twisting, right? I cannot have infinite twisting.
Ah,
And
okay.
that led to
So that leads to the rational number.
right, rational
Oh,
number.
okay.
So I asked us three quick but very basic questions. One, so this magnetic charge of a black hole,
Right.
is it coming from movement of something like electrons? That's why magnetic is like how we read it in high school?
Also, all the magnet, that's for when something's moving, always north pole and south pole comes together. So when you have black hole, it's purely magnetic charge. It has to have magnetic field coming from elsewhere, right? So it's through the wormhole, it's told from the other black hole,
So
which has
it
a
has
opposite.
nothing to do with the electrically charged particles?
No. So it's a sneaky way.
Okay. Second, very naive question. Isn't black hole very cold?
No, it can be very hot. It can burn us completely. So most all the
Yeah,
ordinary
so what's the
black holes.
black hole temperature mean even?
So well, that's very easy. So anyway, so black hole temperature inverse of mass. So it's lighter temperature goes up. Now black hole temperature is the thing that same thing as cold. There's a hot thing, then it radiates, and we get temperature. Black hole radiates, and we feel the temperature.
So it's the measurement of the radiation,
Right,
radiation,
from the
Hawking radiation.
Hawking radiation.
And third very basic thing. What is there an easy way of explaining why physicists have this three generation principle that all the matter is generated by these three fundamentals? Yeah, it was in your table.
What
The three particle generation. In that table of quarks and leptons and
Oh,
things
you
like
mean
that.
flavors, three flavors.
Yeah. Why is it three? Where is three coming from?
Or well, we know why, at least it should be three. So that's why Kobayashi Masaoka got the Nobel Prize. So nature, we know we have more baryons than antibaryons. That's why we are there. So there should be some CP violation. And CP violation is only possible when you have at least three generation. which is Kobayashi-Maska mechanism. So if you have two, you cannot generate more variance. So N is in the industry, and the
got it.
nature is extremely economical. I need something, yes, I need the minimum kind of thing.
Got it. All right. With this, let's thank Kimyeong again.
Thank you.